one of the things you can do as a sort of practicing data mining engineer, whatever field you go into, computer scientist, you can build these things, but custom build them for whatever application you're working in. So we did that a little bit with the bike sharing data. And if you build one of these sort of a custom build for a certain area, one of the things you can do is patent that custom build for that certain type of area. So I want to talk a little bit about custom building things for certain areas. I've done sort of a couple of those over kind of my career, 2 or 3 of those. And they're kind of the most fun. Like you whole diagram and you're like, what kind of pieces work together? A little bit like the bike sharing thing. But how do you put these pieces together? I want a random forest here. I want an Adaboost tree there. And I'm going to set up these different pieces to do different things. So I'm going to walk you through one of those that I built when I was a math faculty at RIT that we patented. So I'll walk a bit through one of those. How's that? Does that sound like fun? Patents, by the way, are cool. You can patent. There's a lot of things you can patent, things you can't patent. So I'll tell you a little bit about those. So you're not allowed to patent a mathematical formula, right? So that's not patentable, at least not in the U.S. But you can patent an application of a formula to a specific area. So if you say, hey, you can't patent a method for sorting, right? Well, actually, I'm not sure. You can't patent the math for a method for sorting. But you can patent a method for sorting mail. And so the post office has been in patent sort of negotiations / disputes with people who, like, you're using my method for sorting mail. The standard mail sorting method uses 5 baskets. My sorting mail method uses 4, and it's half as fast. So you save $1,000 a day. You have to pay 25% of that for the patented part that you're using to save that much per day. And there's sort of negotiations like that on sort of monetary amounts. So you can patent a method for sorting mail. It was a patent for a relationship between sensors. And so this was on the Joint Strike Fighter. You've heard of the Joint Strike Fighter, new aircraft, right? So the aircraft, as it rotates and flies, the heads-up display is not on the screen. It's on the pilot's helmet. And his helmet has gyroscopes or sensors that quickly detect its orientation with relation to the aircraft. And so the aircraft has its gyroscopes that know where it is so that you can figure out where to put on the pilot's helmet. All needs to be done, the display, all needs to be done super duper fast or the pilot gets sick from things moving. Right? So there's really fast formulas for doing that. That computation of the relation between sensors was patented by a little company. And so that company went to negotiation with the US government who built the aircraft. Turned out in the end, their patent was not enforceable because they didn't describe the patent as the use of those formulas for sensors with a helmet and an aircraft. If they had said helmet and aircraft on their patent, they would have gotten like $17 million for the patent. But because they said we're just patenting this formula for arbitrary sensors, the patent trademark office said it doesn't apply because you didn't have the specific application. So there's all these things that have to do with patents. It's a good area to be aware of. Yeah.
Is it economy to patent something and also to publish it in that company?
So it's a really good point. So this is the trade-off with patents. You invent something new. When you patent it, you have to write up your best understanding of the build for that thing and share it with the entire world. So put it on the U.S. Patent and Trademark Office. In exchange for sharing that knowledge with the entire world, you get exclusive rights to build it or to require people to pay you if they want to build it for 17 years or depending on some number like that. Without that, people wouldn't be able to share the technologies quickly. They'd be like, well, I can't tell you what I'm doing, but I have a black box that will do stuff. And you can test my black box, but I can't tell you what's inside, so you can't really trust it. And you can't build it in 2 generations. People don't know what that black box, how it worked. So there's like a limited monopoly for time. So standard patents, Stanford, kind of big academic, our area patents. Stanford has a patent on the search engine stuff that went into Google. So all the Google, their PageRank algorithm was patented at Stanford. So a lot of the Google stuff goes back to where it was developed. The gene gun that does genetic engineering for plants that allows the world to be fed. Without it, probably couldn't feed the world population. That was developed at Cornell, invented at Cornell, and they patented it there and then sold the patent to a tech company. I forget who. So sometimes when you're on the wrong side of a patent, it's annoying when you want to use something that's patented. That's frustrating. As a society at whole, they add terrific value. I have friends who study technology areas of other countries, and they say one of the problems with other countries is people can invent stuff, but it gets taken by everybody and the government right away because the government doesn't enforce patents or private property. And so there's very little incentive to invent things. So patents protect the little inventors. If you invent something and it really is useful, then you can get the value out of it without having to be the big developer company. And just another thing for patents for between private companies, the negotiations get really expensive between the government and individual companies. They're like managed, so they keep them smaller. And with private companies, if somebody uses somebody else's patent, they have to pay lots of damages plus the price. With the U.S. government, if the U.S. government, like the post office, was using something, they don't get charged like penalties for using it. They just have to pay the appropriate fee. So there's a percentage. It's semi-standard. You know, there's modifications on the computation, but they have to pay the appropriate fee. All right. Okay, so I want to talk about spectral imaging. So hyperspectral imaging is just my favorite area. This is where I got into sort of the data area, data mining community. So if you look at an orange, there's lots of different colors of lights that hit the orange. What gets reflected off is mostly red, some green, and a tiny bit of blue, and that's why it looks orange to us. An apple, lots of lights hit it, gets reflected not much blue or green, and lots of red. Similar for grapes. And so we can plot what's the spectrum from each of these, and that's a plot of the percent of light that's reflected as a function of the wavelength. Here it's red, green, blue, or you know, if we had numbers with those that measure the nanometers for the wavelengths, we could plot those. When we want to do material identification, okay, so we can take red nylon. So here's red nylon, yellow nylon, red cotton, and red nylon. And then we can take those and put those in a lab that measures not just the visible colors, right, red, green, blue, those are what we see, but lots of infrared colors. And those wavelengths of light in the infrared will measure the chemical bonds within the materials. And so this plot here, that's the yellow, and these are the red materials. And you can see this area right here is the visible color. The yellow is going to reflect lots of green as well as red. The red ones don't reflect much blue or green, but they reflect lots of red, which is why they jump up at that point. Over here, you'll notice there's a different trend. These wiggles through here indicate that the yellow is a nylon and the red is a nylon, and then the cotton has a different set of wiggles out there in the infrared. So this side, actually the physics is cool. This side has to do with photons hitting electrons and electrons jumping between levels. Over this side, it has to do with photons at these wavelengths, which hit the chemical bonds and make the bonds vibrate. So that's why we get a different set of reflections differences over there. And so when you're doing spectral measurements, your input variables are 200 values or whatever your resolution is, and then your output variables, or the input variables are reflected, percent of light reflected back over those 200 different values. So if you find an object in your backyard and you're like, I think this is a Civil War belt buckle, you'll bring it to a lab somewhere, they'll buff it a little bit, they'll shine light on that metal and measure what's reflected back. And they'll be like, well, that's 87% tin and 12%, I don't know, whatever. It wouldn't be aluminum, but copper? I don't know, what would they make it? And so, yes, that's the proper combination. So what they do is they measure the light off that belt buckle, then they do a linear regression against their laboratory measurements of pure tin and pure copper. And they say, okay, these abundance coefficients times these lab measurements will get you what you've seen. And so what we often care about when we're doing spectral imaging or hyperspectral, when you've got lots of wavelengths, is we'll have the sun shining down, we'll have some satellite or a flying sensor on an aircraft that measures the reflectance of the light that comes back up. And so light comes down. If you imagine a pixel like right here, the light would come down, 15% of the light would hit my laptop and reflect up with a plastic type of spectrum. 18% would bounce off whatever this tabletop is, and the rest would bounce off the floor. So up in the satellite for that pixel, you would see this linear mixture of these different materials that are on the ground. And so here's an image that we collected out in Montana at RIT. And this is what grass out in the field looks like. And those are reflectance levels for soil. And then over on the red over here, this is grass, and then there's a little bit of red nylon in it. But it's 80% grass and 20% red nylon. So you don't see much of it. So the mixture over there looks a lot like the field grass here. You notice This goes high bumping green, comes back down. This has a high bumping green, and you can barely see it from probably where you are, but the little tiny bump in the red there. You don't see the nylon features out there, but if you could pull out the grass, then you could see the little nylon features out there. Okay, so here's an image over Cuprite, Nevada. I think it's Nevada. I'm going to pretend that's correct. Maybe it is. Cuprite, Nevada. Bunch of minerals. What we're seeing is not the red, green, blue that you would see visible light if you went there. What we're seeing is some infrared lights where the minerals, where the reflectance of the minerals matters more. And so what this plot is, this is the percent reflectance across these wavelengths. So it's from 2 microns to 2.5 microns, and or 2,000 nanometers to 2,500 nanometers. The visible in this plot would be over here. The visible is 450, 550, and 650 nanometers. And so we get these different colors based on the different minerals here. And this is great for mineralogists or geologists who go, I want to find this type of mineral in this area. It's also a really good tool for people who want to look for gold or oil or other natural resources, because they can quickly go, okay, these types of minerals on the surface mean that you have certain types of stuff going on underground, so we want to find these surfaces, so they fly back and forth and look for the stuff they're looking for. So one of the tools here, this is a software put out by a software company I worked for a brief time, will allow you to do linear regression on every pixel in the image against some library of basic minerals that you know. So this is the U.S. Geological Survey's library. So this is all the minerals that they've measured that are delivered free with the software. You can buy those off the internet. So these are a couple of different mineral spectra. And so it is, we see, it doesn't look great on there, sorry. We see some spectrum in the ground, it has bumps and wiggles, and we're like, does this line up with something I know? Well, it's a little hard to search through on your own. So what we can do is we can do linear regression on every go under spectral, mapping methods, linear spectral unmixing. So we're going to do a linear regression between every pixel in this image and a couple of the minerals that are known to be in this area. So first we have to tell the software unmixing input file. So this is the image that we're telling we want to do unmixing on. And then we have to tell it what minerals we want to unmix with. And so I picked out 3 minerals, alunite, calcite, and chlorite. And then say apply them to this image. And so here's the output, and it comes out as a new image. And we can say I want to display this new image. Red is going to be alunite, green is going to be calcite, and blue is going to be chlorite. And so there's the output. Right, and so, everywhere that's over here in green was red, blue, green was chlorite. And everything that was red tended to be alunite, and calcite was the blue. And so if I click here, Z profile, what I get is this little mound here. Well, let's see, was 35% alunite and basically 0% this and maybe 9% of the other stuff. So we can get the constituents of the minerals that are on the ground across the whole image. Okay, that's kind of nice because that lets us do mineralogy and geology over a whole area. It used to be people would have to walk around, geologists, with things and take samples. Another thing we can do on here is we can do anomaly detection. And remember I said that Malhava-Novus distance anomaly detection is a different name in every field, and in this field it's called RX anomaly detection. And so we can say, I want to take this and apply it to the Cuprite image, and the output I'm just going to store in memory. And so there's the output from the anomaly detection algorithm. And now the brightness here corresponds to the distance away from the mean in these sort of pseudo standard deviations. And so I've got some object up here that's bright. And so what I can do is put the cursor here on this object. And I can tell the screens to match each other. So there's some object here or some mineral that's really rare in the image right there. We've done anomaly detection. We found that. And I want to try to do some unmixing to figure out what that is. And I'd like to do a spectral unmixing, but I have 1, 2, 3, 4, 5. What do I have? 200 different materials in my library. So I'd like to say this pixel here, it's some linear combination of the 200 materials in my library, some mineral that's in there. And some of these have like 4 or 5 samples of the same mineral. So some of these are highly correlated to each other. So I want to do linear combination of these, but there's a lot of correlation in my library, and I want to figure out what linear combination is giving me this odd pixel here. And let's get a plot of that pixel. So that's the spectrum that's odd. This plot is rare in the image. What's my favorite tool for doing regression with what's my favorite tool for doing regression with a really complicated set of inputs? Not rainforest. My favorite regression method. Begins with Bayesian and ends with averaging. Yeah, BMA. That's my favorite. Okay, so this is a piece of software I wrote for the company. So it does Bayesian model averaging. So we say we have to pick the library that we're going to use. That we're going to take linear combinations of stuff in the library, and I saved a copy of it here. Then we have to tell it which image we're using. So that's the image. Then we have to tell it what signature I want to unmix, and there's the signature we're unmixing. And so what it does is it says, here's the spectra that are likely to be in here. Then here's the top 2 spectra. This column has a likelihood from the Bayesian model averaging. The top most likely spectra are this one, which is stibite. And this is another measurement also of stibite. The likelihood for this is 0.51. The likelihood for that is 0.34. So taken together, the probability that it's stibite, because we can add these because they're really the same material, probability that it's stibite is 85 or 0.85. That's the probability it's stibite. So I have all, I can go down the list and see what else is in there. And these are all the ones that are really low probabilities. And I get these 2, which are the best probabilities. And so up here I can look at, here's my pixel in red. When I do unmixing, this algorithm will also find pixels nearby and try to remove them to get you the underlying pixel, the material that you're looking at. So the things that aren't in there is removed from the mixtures. And so the blue is the best match to the material I'm looking at, which is the green. So the blue and green match, and I'm like, yep, that's stibite. If I go down the list, I could look at some of these other ones that, that are possible but have really low probabilities. And for this one, I can see why the green here kind of tries to match the blue a little bit, but there's some wiggles that show me a mismatch. So that's why these are less likely. Anyway, so the point isn't to talk so much about spectroscopy, which is matching the wiggles. The talk is, the idea is, wow, I found something that was really anomalous with the anomaly detection algorithm we saw before. It's the Bayesian model averaging that gives me probabilities that I can combine and say, yeah, this is really likely to be stibite. And I've done regression against 250 predictor variables. regression against a mixture with 250 possible elements that I'm going to do my regression with. Okay. So what's the patenting part? So that's the goal in that field, is to be able to identify, classify large areas, but also identify small things and then identify those. And so one of the algorithm we patented, it outputs an HTML page for each image. So this is a large area. And there's a little city here, and it's mostly mountains and things around the city. And then we told the algorithm, find the red nylon. And so there's a red nylon fabric somewhere in there, and it's, I don't know, a couple square miles or something. And the red nylon fabric's only a little tiny thing. And so it adds a list of, I think I found something here, something here, something here. When you click on those, it gives you all these sort of outputs that you'd like to have. That's the RGB, and this tells me that's where it thinks it found something. And then I can go, oh yeah, this has the right matches for, this is actually the red cotton. Those are red cotton little matches. So yeah, so this is, that's definitely red cotton, and I've got that. So it goes, it's really a multi-stage algorithm. It searches the whole thing, and it finds little pieces, then it passes them to another stage and does several processes on those, and then passes them to another stage. So it's like a big linear regression followed by two other types of linear regression with maybe some Bayesian model averaging as well, and then it sends those results to one final thing, and that's what gets output as the list. So that's the type of thing you can patent. If you've got a bunch of stages, they really give you something that's different, and that's the, like if you have a long term to build something, you want something really high accuracy, that's the way to build it, to look at how can I break it up in a couple pieces. Right. Questions? No? Yes, no? Okay. Yeah. That's about all I have. Let's go back to.
I have a question for patents now.
Let's end up on that picture.
Not as much with the model itself.
Sure,
If someone
yeah.
added an additional element to your process,
Yeah.
tiny piece.
Yep.
Does that warrant a new patent?
So, okay, yeah, so this is a really interesting thing. So the way a patent works, when you write a patent, you have like what looks like a paper that you'd publish, it describes it. Then you have these set of claims. This is what I claim, this sort of two-sentence description. So if somebody does something that repeats one of those claims, then that would infringe on that patent. They can't do it without permission. Now, if they did those claims and added something new to it, they could patent that new process together with those claims. They couldn't do that new process unless they had your permission, license to use it, and you couldn't do those claims with that new process without their permission. So you'd have to teamwork together. One of the standard things that really, when patents work well and companies work together and sit and talk, like your phone, there's lots and lots of patents that go into a phone. Same thing with wireless networks. If all the companies said, I want every penny I can get out of that patent, phone would cost more than a car because of the number of different patents that go in there from different companies. Same thing, wireless networks, we wouldn't have one convention. We couldn't all hook onto the same wireless network. There'd be like 20 different conventions, and you'd all, like, oh, I have the Samsung XYZ patented, and they'd be like, no, I have the Microsoft, we can't talk, I need to go to my own different coffee shop kind of a thing. Right, so that would be terrible for everybody and society. So what often companies will do is what's called fair and reasonable rates, meaning we're going to like work as a group to get something that's fair, we're going to get something that's reasonable, and in the end is better for us. We're going to cooperate to get a reasonable price on the object so actually people can buy phones, which in the end is better for everybody. But yeah, it's a, yep. So often people patent doing something earlier with a second stage. That's pretty common. Yeah. The criteria are, 3 criteria for patent. It has to be novel, meaning it's new, like nobody's done it before. Meaning, really, somebody did it in the garage, that doesn't count against novel, but if nobody's done it and published it. It's not in the public knowledge. It has to be not obvious. So if you can't patent like, oh, I'm going to use support vector machines from the carrot package, and I'm going to patent that with a parameter of 17. You know, that you can't patent because anybody would just think, oh, I might try 17 as that parameter value. It's like, to a practitioner in the field, that's not, all right, that's an obvious thing to try. Right? So it has to be new, not obvious, and useful. So it has to actually have use. So you can't patent a way to flap your wings and get to Mars, right? I mean, nobody's done it before, definitely new, and you know, nobody would think of it, but it's not useful, right? So.